Last week, we talked about equilibrium of a particle. So you may have felt a little bit, maybe not confused, but maybe disappointed that the first 4 weeks we didn't actually talk about statics. Instead, we were reviewing these things like vectors and these operations. But last week, we finally started to talk about statics. And we talked about statics by going over the equations of equilibrium. Now, I normally don't encourage people memorizing equations. However, the equations of equilibrium are easy enough that all of us can memorize them, right? If you guys remember, we mentioned that the main equation of equilibrium was that the sum of forces in a system, in a static system, equals 0. However, we also mentioned that we can break them down into their Cartesian coordinates, where sum of forces in the x direction, sum of forces in the y direction, and sum of forces in the z direction equal what?
0.
That's correct, 0. Okay? So these are the equations of equilibrium. Now, if you watched the video last week, I did mention that these equations, we're missing one of them. Okay? And this week, we're going to go over that missing equation of equilibrium. So in order to do that, I want to introduce a new concept. Maybe not new for you, but definitely new to this class. When we have forces, we typically visualize or study or analyze those forces as if they were acting at a point. Force is a vector, right? And if we are applying a vector on a plane, the vector will act at one point. However, sometimes it's not enough to know the magnitude of the force. We also need to know the location of the force, because the location may actually influence, right, or affect how we react to it. Think, for example, of yourself carrying, let's say, I don't know, maybe a tray. Think of a tray with a lot of food items on them. If your tray is close to your center of gravity, it's close to your body, and your items are well distributed, you have to apply whatever amount of force you need to hold the tray steady. Now, ideally, right, if we're looking at statics, the equations of equilibrium tell us that the sum of forces in the y direction equals 0, which means that the weight of the tray and its contents should be equal to the force that you're applying. But now, what happens if you hold the tray by its longitudinal end, and then you place all of your food on one end of the tray, and the end that's furthest away from you? I have my tray, I'm holding it by the long side, and then I put all my food at the end of the tray. Do I have to apply more force or less force? Is it heavier? Is it not heavier? What's happening here? Think. Yeah? Okay, there's more torque, right? So it's not that the tray is heavier, the weight is still the same, but now in addition to experiencing that vertical force, that weight, I'm also experiencing a rotation, a torque, okay? That is the definition that we're going to use for what we call a moment. So a moment will be our property that describes the tendency of a body to rotate. Another word for that tendency of a body to rotate is, as Sophia said, a torque. Okay? So if a moment describes the tendency of a body to rotate, I think we can visualize, at least conceptually, from a conceptual level, how to relate that force to that moment. And you can go back to the tray example. You can use any example, right? In any example, the further, right, your weight is from your body, for some reason, the greater the torque. Okay? If you don't believe me, just try it out yourself, right? Hold two weights close to your body, hold them away from your body, and figure out which one is actually harder for you to do. I speak as if I knew what I'm talking about, but as you can see, I do not work out. But if I did, this would be a good example for me to use. Okay? So the moment can be taken to be a relationship between a force and perhaps the location of that force. And that location will be quantified as a distance. So in order for me to define my moment, the first thing I want to do is I would like to define where my point of interest is. Let's say I'm applying a force. The force vector F. Okay? if I apply the force at this point, this little green point, will this force cause this point to rotate around itself? So if this is a coin and I'm applying a force right on the center of the coin, will the coin start to rotate? No, it wouldn't, right? However, if I were to apply that force, instead of on a coin, on a small coin, if I were to apply the force on a stick, on one end of the stick, do you think there would be some tendency to rotate around the other end of the stick? Mm-hmm. Yes, right? So the moment, which again is the tendency of rotation, the tendency of my object to rotate, will be quantified. Will be quantified as the distance, right, between my point of interest and my force. And this distance, I'll just call it d. So this distance multiplied by the force is equal to my moment. Now, if you've taken physics and you've studied torque before, you'll see that the equation is very similar, right? Torque is a force times a radial distance. Moment is force times a distance as well. A linear distance, but nonetheless a distance. Okay? So moment is equal to force times distance. And what does this tell me? The further away my force is from my point of interest, right? That means the greater my distance, and so the greater my moment. So what this tells us is that forces, we don't only have to care about their magnitudes, but we also care about where, right, where in my body they are applied. When I say body, remember week 1, I mean an object that consists of multiple particles together, okay? So moment is force times distance. The greater the distance, the greater the moment. The greater the force, the greater the moment. Now, I'm making an example here with a stick. However, the tendency of rotation doesn't necessarily need to include a body. In other words, the force doesn't need to be applied, right, on a body such as a stick. So what I'm going to do is I'm going to define what's called the line of action of a vector, and in this case, the force vector. To make my definition as simple as possible, the line of action is simply an axis through which my force vector passes. If you want to visualize it graphically, your force vector, just extend it, right, to the left or to the front and to the back as far as possible, and that line is what we call my line of action. So the moment, right, is equal to the magnitude of the force times the distance between your point of interest and the line of action of your force. Now the question is, how do you measure that distance? Would I measure my distance like this, like this, like this? So just to make things easy for you, you will always measure the distance between your point and your line of action as a perpendicular distance. So if you have a long line of action, you want to find the moment about a point of interest, you want to choose the distance that provides a 90-degree angle between your point and the line of action. And this is essentially the shortest distance, right, to the line of action. Okay? So shortest distance, 90-degree angle, and that is how we calculate moment. Now, I know we've seen this before, and I don't want to feel like we're just repeating everything that we've learned in previous classes. So what I'm going to do now is I would like to present moments, right, in the context of everything we've learned about vectors in the past couple of weeks. But before I go that deep, I want to make sure that we understand, or that we come into an agreement, right, of some conventions that we're going to use in this class for moments. Now in forces, we've already defined that if forces go along the direction of an axis, we're going to call them positive. And if they go in the opposite direction of the axis, we're going to call them negative. Typically, and this is not always, but typically we set to the right as positive, right, and up as positive, and then to the left and down as negative. But this is not always the case, but that's a typical thing. For moments, we're going to do something similar. For moments, we are going to set our counterclockwise rotation as positive and our clockwise rotation as negative. Now, I don't want you to get too worried about memorizing these, because we're going to use moments in the context of equilibrium. And when we're dealing with equilibrium, it doesn't really matter which side you choose, as long as you have a consistent definition of what is positive and what is negative, your answer should be the same. In other words, if you're working on a problem on your homework and you accidentally flip these two terms, you should still get the right answer, because everything equals 0, right? So in the end, you should still get the correct answer for your moment. Okay? Obviously, we're going to have some negative signs in there that we may need to talk about. But for now, what needs to be clear is that whatever you choose positive when you start a problem has to be positive until you end the problem. You can't flip midway. Okay? But within each individual problem, there's always some leeway. Some fields of study prefer the clockwise rotation to be the positive one. Fields like mine, we prefer the counterclockwise rotation. So don't get too worried about memorizing these. Just work on your practice problems, and these two terms will stick to you, and you will come up with a consistent way, right, of writing down moments. Okay? Now, because moment is the distance that forms a 90-degree angle with the line of action, we are going to have to deal a little bit with our geometry. Because sometimes this distance may not be a very obvious distance. For example, if we're trying to find the moment, say we have a force acting on this piece of wood. I'm going to draw my little force vector here. And I have this distance, I'm just going to call it A. And this distance, I'm going to call it B. If I want the moment, right, the tendency of rotation that this force causes about this point, what will my distance be? My distance D, right? What would this D be in order to calculate moment? Moment equals F times D. So what is D? Is D equal to A plus B? No. So what would D be equal to given this information?
A squared plus B squared.
There we go, right? So when we get to problems where our distances are not as straightforward as we want them to be, we need to bring out our geometry. In this case, we have what's essentially a right triangle, where we know the base and we know the altitude. Therefore, if we want to find the distance D, the distance D will simply be equal to the square root of A squared plus B squared. That's not always the case. Sometimes we don't have right triangles. Sometimes we have other methods. But what I want to get at is that we will have to bring in our geometry sometimes in order to use the correct distance D. Sometimes this distance is not that easy to find. And when that's the case, we typically like to break down our moment into its components. Now, you know how to break down forces into components, right? If I give you a force in Cartesian space, that's x, y, z space, could you give me its x, y, and z axis? Assuming that I give you the angles that you need, could you give me the x, y, and z components of that force? If I give you a force? Yeah, good. We're going to do something similar with moments. Sometimes, if it's not easy to quantify the distance between the line of action of a force, I'm going to draw it this way this time, and your point of interest, it may be a little bit easier for us to look at the components of the force instead of looking at the force as a whole. In other words, if we set this as my x-axis and this is my y-axis, and this is my force, I can find the x component of the force and the y component of the force and calculate my moment as the sum of the moments of these two individual components. So why would that be easier for us? Think of it this way. We have an x component of the force whose line of action now, right, is no longer, right, it's no longer this diagonal line of action, but rather the line of action of my x component becomes this horizontal line. Okay? And we have a y component whose line of action is no longer diagonal, but instead is a vertical line. Now, we mentioned that the distance d is the distance that gives you a perpendicular, a 90-degree angle between your point and the line of action. So if I want to find, once again, the moment about this blue point, and instead of using my total force F, I want to use the components of my force, then I can say that the moment is equal to, let's say, the y component of the force, F sub y, times which distance? What do I have to measure to multiply it to get?
Horizontal distance.
Exactly, the horizontal distance, right? So I call them A and B. I'm going to use the same terms again. So Fy times A. Now why A? Because A is the distance that gives me a 90-degree angle between my point and the line of action of the force. Does that make sense so far? Okay. Likewise, if I want to find the moment from my x component of the force, I get my force along the x direction times the distance that gives me a 90-degree angle with the line of action of that force. And that distance, I mentioned, is b. And now just as a little review, Noah,
Yes.
is the y component of the force causing a positive or negative moment?
The x component, you said?
The y, the vertical component of the force.
That would be causing a negative.
Why so?
Because based off the, are you looking at it at the blue point?
Yes, blue point. So this is a good thing to look at. Sometimes it's a little bit hard to figure out where's my positive, where's my negative, right? Particularly if my force is not directly connected to my point. So what I'm going to do is I always recommend my students, particularly my static students, to visualize your point, whatever point it is that you are studying, as the center of a steering wheel. Okay? And where that force acts on with relationship to your point is where you are moving your steering wheel. So if my point, my blue point, is the center of the steering wheel, and I have a vertical force, right, a force acting vertically to the right, that's essentially the equivalent of me applying my force vertically to the right of my steering wheel. Now if I do that, if I apply a force vertically upwards to the right of my steering wheel, in which direction am I steering my wheel?
Or counterclockwise?
There we go, counterclockwise, right? So is this a positive moment or a negative moment?
That'd be positive.
Good. Does that make sense to everyone? If it doesn't, then do your best, right? But I like to look at it this way because now, if we look at the x direction of force, we have a force being applied on top of my point. That means that I have a force applied on the top of my steering wheel in which direction, left or right? My x direction.
That'd be to the right.
To the right, okay. So in which direction am I rotating the steering wheel now?
Negative.
That's right, in the clockwise or negative direction. That means that my x component of the moment will be negative. Does that make sense so far? So, different ways of calculating moment, right? I have my first method, which is simply force times the square root of a squared plus b squared. Now, this works because my force, right, is acting at whatever angle from my point this triangle provides. However, in this case, where it becomes a little bit harder to figure out those distances, right? It becomes harder to come up with that right triangle. It's easier to just calculate using components, okay? I'm not teaching you different methods because I'm trying to fill your minds with theory. But what I do want to get at is that different sets, different systems, will have to be solved in different ways. Here, it's easy to just use square root of a squared plus b squared because this gives us a distance perpendicular to this force, similar to a right triangle. We can't really say that here because if you look at my force, my line of action actually has a distance from here to here, and then it becomes harder to come up with a triangle. You have to do more geometry. So in some cases, it's easier to look at components. In some cases, it's easier to look at geometrical or trigonometrical relationships.
Quick question for you.
Yeah, go ahead.
On the second example in the way of calculating it,
Mhm.
you have the negative of x of b, or minus, is that because it is heading in the negative direction?
Yep.
Or the clockwise?
Yeah. So my Fy, right, is my force that causes a counterclockwise, so that's positive, right?
Okay.
But then my Fx causes a clockwise rotation. Again, steering wheel, center of the steering wheel. So clockwise, so I add a negative sign.
Okay. And so that will just vary depending on the direction.
That always varies depending on the direction. That's correct. So don't memorize this equation, right? Don't just write this every time you see a problem like this. Instead, look at the directions, and based on those directions, make a decision on which sign to use, either positive or negative. I want to apologize to this section of the classroom because we're only recording this side of the board, so I'll be writing on this side, okay? This is moments in two-dimensional spaces. Now, what happens when we're looking at three-dimensional space? Of course, we know that moment is just f times d. So if we're looking at 3D space, we just need to find that d as a three-dimensional, maybe position vector, right? Maybe a three-dimensional line. Now, you'll see that in two-dimensional spaces, it's actually easy to use scalar analysis. Even though this force is a vector, because we know forces are vectors, we are only looking at the magnitudes of the force because we can assign positive and negative values just based on looking at the axes, right? But it becomes a little bit more complicated in three-dimensional space because in three-dimensional space, how do you know what is a clockwise? How do you know what's a counterclockwise, right? It becomes a little bit harder because now you don't have just two dimensions. You have three dimensions. You have three axes through which you can rotate. Everything just starts to become more complicated. So, in order to avoid confusing you, I will give you the equation first, which I never do, but I'll give you the equation first, and then we'll talk about what it means. So in two-dimensional space, we said that moment was equal to force times the distance. However, in three-dimensional space, we'll say that my moment, which is a vector, will be equal to the cross product of the distance, which is measured through my position vector, times my force. So cross product of distance and force vector. Now we've talked about the dot product back in week number 3, right? Week number 4, we talked about the dot product. And we mentioned that the dot product was essentially a way to multiply, right, the effect of one vector on another. And the dot product in our explanation basically looked at cosine, so components of one force along the other. And we mentioned that when we're looking at those components of one force over the other, we're essentially neglecting the component of the difference between the two vectors. In other words, if we were looking at two vectors, A and B, with an angle theta, my dot product said that A dot B was simply equal to AB cosine theta. What that means is that you have A times cosine of theta, so the component of A, or the projection of A along B, and then multiplied by B. However, we're neglecting this difference, this component. And that's where the cross product comes in. The cross product will now look at the perpendicular component. So while the dot product looks at the parallel component, the cross product will look at the perpendicular component. So we will define the cross product of two vectors as the product of their magnitudes Dot product, we're looking at the effect of one over the other, so we use cosine. Cross product, we're looking at the difference or distance between the two, so instead of cosine, what are we looking at? Say it again? Sine, that's correct. Times a unit normal vector. Now, why do I have this unit normal vector? Because we'll see when we define our cross product that moment is a vector. And we have two scalars, a scalar, so we need to multiply by a vector in order to turn it into a vector. Now, from week somewhere between 2 and 4, I mentioned that I really want for you to visualize vectors as products of magnitudes of scalars, right, times a unit vector in the direction of your vector. And again, the reason for doing that is so that we can visualize these types of physical vectors and understand that what we have here is essentially the magnitude of the moment. And what we have here is simply the direction. A unit vector that tells me the direction of the moment. Now, moments in 2 dimensions don't really have positive and negative directions. They have clockwise and counterclockwise rotations. So the way we're going to express this moment as a vector in 3D space is by saying that if we look at the axis that passes through my unit vector n, this moment is positive if it rotates counterclockwise to this axis, or about this axis. So I'll explain myself. If I were to calculate the moment in 3-dimensional space, r cross f, I get this equation. And let's say that this n hat, this unit vector n, is here. That's my unit vector n. This is it. Just a small vector pointing directly forward. If my moment, if my rotation is counterclockwise to this vector, then it's a positive moment. If it's clockwise to this vector, it's a negative moment. Likewise, if my n is here, same thing. If it's counterclockwise to this vector, it's a positive moment. If my rotation is clockwise to this vector, it's a negative moment. Now, this may take a little bit of time and a little bit of practice to get used to. So we will do examples. Don't worry. We will look at a couple of examples to help us kind of visualize or get familiarized with this notation. I want to get you through the hard stuff first, the derivations, the equations, all that stuff, so that we can then look at examples knowing everything that we need to know in order to solve them. From your, what is it, algebra, physics, I don't know, from your whatever class where you deal with vectors, does anybody remember how to solve a cross product?
Matrices? Yeah.
Yep. You create a matrix, right? You take the determinant of the two vectors. So just like we have with the dot product a second formulation, remember we came up with a formulation of ax bx plus ay by plus az bz. Just like we have this for the dot product, we are going to come up with a formulation for the cross product as well. Now, from your courses, your previous math or physics courses, you know that cross product is the determinant of two vectors. And I don't think I'm the best person to explain the physical meaning behind this. So what I will try to make clear is that moment is the tendency of rotation. So if moment is the tendency of rotation, then the cross product quantifies that tendency for us. In other words, if you look at this definition of the cross product, what angle do you think gives me the highest moment, the biggest amount of moment? So we have my cross product definition. What's the angle between two vectors that will give me the biggest number here? 90 degrees, right? Thank you. Because at 90 degrees, the sine of 90 is 1, and this is the largest number. What that means is that if two vectors are perpendicular to each other, that's the most amount or the most tendency of rotation we can have between the two. The closer the vectors are to each other in direction, right, the smaller the moment. So the smaller tendency of rotation. When you get to your more advanced classes, particular fluid mechanics, which is my favorite class to teach, we use the cross product to determine the vorticity, that is the rotation of a fluid. So the formations of vortex or vortices, right? So things like whirlpools, we look at those in the context of a cross product, because cross product is essentially the tendency of rotation. So now let's just go ahead and solve this cross product using our determinant. So just as a recap, right? We know that the position vector is simply equal to some x component in the I direction plus some y component plus some z component. Likewise, we can say that the force has an x component, a y component, and a z component. So given this definition, I would like to go ahead and calculate the cross product. And I can calculate the cross product by taking the determinant. So I will say that R cross F is equal to the determinant of the two vectors. Can somebody help me write this determinant? How do you write a determinant between two vectors?
So ijk is going to be on the top.
Okay, so you have your directional vectors, that's correct.
And then, correct me if I'm wrong, but I think R goes in the middle.
Yep.
So Rx, Ry, Rz. And then on the bottom is the Fx, Fy, Fz.
And this is actually very important. I'm glad that you mentioned this. For dot product, we mentioned that it was commutative, which means that A dot B and B dot A are exactly the same thing. But for the cross product, the vector that you write first is the one that goes first, right? The vector that you write last goes last. And this is very important, because if I were to write F cross R, this would be a different result, okay? So now, what does this give me? How do we solve the determinant? If you don't remember, it's actually not that complicated. So if you look at this matrix, don't feel scared. It's actually really simple. There's a million different ways of explaining how to solve these, but the way I know it is you take your first directional vector, and then you take the matrix of the other components. So if you choose I, you're going to ignore anything in the column and in the row of I. Then you choose everything else, okay? So you choose I, ignore anything that intersects with I, choose everything else, and then write down. I'm going to write the whole thing. You don't have to, but write down the determinant. So I have matrix of Ry, Rz, Fy, Fz. Now this step of writing those little matrices, you can skip it, right? I'm just writing it so you know where they are coming from. And then you multiply it times I. Here's where things get a little different. Some people like to say plus this other vector. Some people like to say minus this other vector. So I'm just going to explain twice. I'm just going to explain it both ways. So we have our first vector, minus. Okay, so we start with plus. Then for our middle vector, we go with minus. So minus, okay, my j vector okay. Now when we chose I ignored everything that intersected with I. When I choose j, I'm going to again ignore this row, and I'm going to ignore this second column, and instead I will focus on these two columns. I'm going to start filling this up with colors, so it may get a little bit complicated. But essentially, what I have is the following little matrix of Rx, Rz, Fx, Fz. And all of this multiplied by j hat. We started with plus, then minus. Now what? Plus. Yeah. So plus, and now I will choose my k vector. So if I choose my k vector, and I'm going to let you figure this one out. If I chose I, the first column, then I picked everything on the second and third column. If I chose j, the second column, then I picked everything on the first and third column. So if I'm choosing k, what will I pick? Exactly. My first and second columns are simply my x and my y components. So plus my little matrix of Rx, Ry, Fx, Fy. And all of this multiplied by my k unit vector. And what we end up here is a vector, right? We have a x component, that's I, a y component, that's j, a z component, that's k. And to find the magnitudes of these components, we just solve this little matrix. And solving matrices like this is actually pretty easy, right? You take, just make sure you're all following me. You take this over this minus this over this, okay? So 1, 1 times u times 2, 2 minus 1, 2 times 2, 1. So it's like an x. It's like a cross. Oh, you see what I did there? Cross product, okay? So we get Ry times Fz minus Rz times Fy. And all this multiplied by my unit vector in the direction of x. Likewise, minus, we have Rx Fz minus Rz Fx. And finally, again, we do a cross, Rx Fy minus Ry Fx. And this is the cross product. This is the moment between, or sorry, the moment that a force F acting at a distance r from a point causes. We have an I component, we have a j component, we have a j component. And what does this mean? That the rotation will be this strong about the x-axis, this strong about the y-axis, and this strong about the z-axis. Now, how do you find this direction in? The same way you find the direction of any force in 3D space. Remember your forces, you have an x component, a y component, and a z component. And I can always ask you to find the magnitude and the direction, right? How do you find the magnitude of this force? Okay, right? Fx squared plus Fy squared plus Fz squared, and then take the square root. Likewise, can you find the direction of a force? In 2D space, can you find the direction? Yes. Inverse tangent of y component over x component. We can do the same thing in 3D space. It's the same concept. The vectors are still the same. It's still vector theory here. If I want the magnitude of my moment, I take x component, square it, add it to my y component squared, add it to my z component squared, and I take the square root of that, just like with forces. And if I want the direction, once again, I can use my angles to find that direction. Now, I'm going to be blunt. When we're dealing with 3D space vectors, instead of complicating ourselves to try to find unit vectors and directions, for the most part, not always, but for the most part, I'll try for you to look at rotations in terms of x, y, and z directions. Not always, for the most part. We will get 1 or 2 problems where we actually practice coming up with the actual direction of the vector, just as a general vector practice. But this should be good enough, because this already describes to me the tendency of rotation of that force about a point. Yeah?
So on your y component to the j component, it's negative off of your cross product. What does that mean in practicality? Does that mean that it has a tendency to circle the other way?
Yes and no. So once I plug in all my values, because sometimes you can't have negative values here, once I plug in all my values, right, if this magnitude is a positive number, it just means that rotation is counterclockwise about the x-axis, right? If this one, if I were to punch all these numbers together, if this one were a negative number, that means that the tendency of rotation is clockwise about the y-axis. So the positives and negatives here function as if they were scalars, right? Clockwise, counterclockwise, but about different axes, right? We have x-axis, y-axis, z-axis. And whether it's positive or negative on these scalars really depends on whether the direction of rotation is clockwise or counterclockwise on the individual axis. Okay? Does that make sense? Good. So, moment in 3D space. We've talked a lot, I know. I mentioned that there's a different way of calculating this, so I'm just going to go over it really quickly. The way I learned to solve this is the same thing for the eye. This was when I was your age. Ew. And then for the y component, typically I would just start here and just invert this matrix. So I would essentially extend my matrix by simply rewriting the first column, and then I just have my little matrix here. So I would say plus RZ, RX, FZ, FX, J, and then this is the same thing. And you choose whatever works best for you. I kind of prefer this one because it allows me to keep all of my terms positive, at least until I plug my numbers in. But it does give me a little bit of extra work of writing the column again. But it doesn't matter which one you choose, your final answer will always be the same. Because notice that if you were to multiply this -1 times this term, you just get the positive of this matrix. So it's exactly the same. I mean, whatever's easiest for you, right? There are other ways to solve determinants, but I think these two are the ones that I like the most. If you know this and can just write this directly, that's fine. If you need a little bit of practice, then maybe try practicing by writing the little matrices and then crossing them, okay? Any questions before we do an example? Okay. We have 25 minutes. I'm going to try to do a couple of examples, and if we still have time, then we can just keep going, because this is, like I said, a very, very short chapter on moments. So let's go ahead and do problem F4-1 from the book, Fundamental Problem 4-1. Now, because you've already seen moments before, I'm going to try, right, to let you take the lead in solving this problem. So we're looking at F. We're looking at F4-1, and essentially we have our little block of wood, just like in our example. And we're given dimensions of 5 meters and 2 meters. We have a force of 100 newtons acting at the end of our block with a slope. I'm not giving you an angle, I'm giving you a slope of 4 horizontal for every 3 vertical. Okay? Now the question is, what is the moment that this force, this 100 Newton force, causes about my origin point if I define my origin right at the wall? So, like I said, I'll let you take the lead. How do we solve this? What do you think we should do? Would it be easier to do a right triangle? Not sure. Would it be easier to do components? What do you think? Components? Okay, so let's do components. So how do we solve this problem then? We say let's split the force into its components. So I'm going to redraw my vector here. I have a 100 Newton vector. We know the slope of 3, 4, 5. How do I find the x component of that force? I don't give you an angle, so you can't use cosine, but maybe you can. What was the definition of the cosine of an angle?
So you need to use the ratio of the hypotenuse.
Yeah, that's correct. You want to use a ratio, right?
Yeah.
Thank you, Jenny. We want to use a ratio, and it looks like we have some confused faces. So if you don't know why we have to use a ratio, think. Remember? So katoa, didn't they make you memorize this in high school or middle school, right? At least they made me memorize it. The sine is equal to the opposite side over the hypotenuse. What is that? A ratio. The cosine, right, is equal to the adjacent side over the hypotenuse. The tangent of an angle is equal to the opposite side over the adjacent side. So what does this mean? For my triangle, for any triangle, the sine of the angle is equal to the opposite side over its hypotenuse. The cosine of my angle is equal to the adjacent side over the hypotenuse, and the tangent is the opposite side over the adjacent side. So what I have here is a little triangle that gives me my slope of 3 to 4 to 5. And how can I find a relationship between my angle and my little triangle? Well, in the x direction, right, if my angle were from the horizontal, the x direction would be f cosine theta, right? If my angle were from the horizontal. And what is cosine? Cosine of the angle is equal to the adjacent side over the hypotenuse. There's our ratio. So we have a little triangle here. We have a little triangle with our angle theta. What's the side adjacent to theta? 4, right? 4 is adjacent to my little angle theta. And what is the hypotenuse of this triangle? 5. Okay? So my x component is equal to f times the ratio of 4 over 5. This is something that's called similar triangles, right? You have two triangles with the same angles that are whose sides are proportional. So similar triangles tells me that the ratio between two sides is equal to the ratio between two sides in the other triangle. Again, this is not a geometry class, so I don't want to get into too many details, but for now, I need all of you to understand why my x component is f times 4 over 5. Okay? So my x component is equal to 100 times 4 over 5. How much is that? 80? 80 what? Newtons. Thank you. Similarly, my y component is equal to my force times what ratio now? 3 over 5. That is correct. How much is that? Units? Newtons. Good. So we find our components. And sorry for that little tangent into geometry, but I need you to understand this, okay? So that you can do well on the next test. So we have an x component, a y component. Now let's just calculate the moment. The moment about that point should be equal to the moment that each component has about the same point. So let's start with the x component. The moment is equal to the x component times what distance? So we have my x component of the force. It acts on the same point. That means that my line of action is this horizontal line. So what's the distance between the point and the x component that I would use? Sorry? 2, correct. And would this be a positive moment or a negative moment? All right, steering wheel. Center of my steering wheel. Here's my steering wheel. Am I rotating my steering wheel clockwise or counterclockwise? My force is pointing to the right. Am I rotating the steering wheel clockwise or counterclockwise? Is that positive or negative? Okay, good. And then we have my y component of the force. And what's the distance to the y component?
5 meters.
Okay, 5 meters. Positive or negative? Steering wheel. Still negative. Notice that my vector is pointing downward, so that means that my y component is pointing down. So I am doing this to my steering wheel. And what do? I am rotating it clockwise. Therefore, negative. Okay? So what does this give me? I have 80 times 2. I'm just going to use parentheses. 80 times 2, negative, minus 60 times 5. How much is it equal to? 160 minus 300. How much is that? Well, negative 160 minus 300. There we go. Can you say it again? And what are the units of the moment? We have newtons times meter. So my units will be newtons times meter. I heard someone say newtons per meter. Remember, per means that you're dividing it by. Okay? Any questions? Okay? It seems like we have a good grasp, at least on two-dimensional moments. Can we agree on that? Does everybody understand why these terms are negative, or do we need maybe some restatement of that? Okay. Think of the steering wheel, or pick any other method that works for you, but have a method that allows you to have a consistent set of signs. Yeah?
So on that steering wheel, I'm getting kind of confused about where I would set that vector for how the steering wheel is going to move.
Oh, so the way I look at it is your point of interest is the center, and wherever the vector is, you just draw a circle until it touches that vector, right? So remember, your line of action corresponds to a perpendicular distance. This is 90 degrees with your line, right? So the idea is that your force should or your line of action of force should always be somewhere in the wheel, okay? But again, if that doesn't work for you, use your own, use any other method. But the idea is that you understand that clockwise negative, counterclockwise positive. And if you get it wrong, you'll still get the right answer, right? You will still, if you were to forget about it and just have both of them positives, this would still be 460. So the numbers will still be right. And because you set your positive as clockwise, then you'll know that it's 460 clockwise. If you want to remove any semblance of doubt, always tell me which direction you are setting as positive. So that when we look at the exam, I say, okay, you get it, right? You just chose a different direction. So in this case, this is negative 460 newtons meters. And in this case, I'm setting my positive as my counterclockwise. Okay? That's all it is, okay? So when I see my negative sign, I know that it's going to be in the opposite direction. I don't want you to get too worried about that, okay? Instead, I want you to understand why we're multiplying the x component by 2 instead of 5. Why we're multiplying the y component by 5 instead of 2. So as long as we understand that, as long as we understand that our distance needs to be perpendicular to my line of action, and as long as we know what a line of action is, then I think we should be good. Any questions? Okay. So if there are no more questions, let me see if I can find another example. Aha. Okay. Let's do fundamental problem F4-13. So we can look at our vectors a little bit. Sometimes, and I'm going to say this from experience, and you can ask your brother because he took my test before, so sometimes it really helps for you to read the entire question before trying to solve the problem. He did say that, right?
Yeah, he said like you kept on the wording of your problem.
Exactly. So normally what happens, and I'll just be frank with you. If I want to have different questions for each student, I normally write kind of like a template where I have all the data I need. And then based off that template, I come up with questions. And they may not use all the information, right? So if we look at problem F4-13 and F4-14, they use the same figure, but they ask different things. And like I said, it's sometimes easier to figure out what they're asking from us in order to not do any extra work. If you do extra work, that's fine. I mean, it shows me that you are very good with moments, but not very good at following instructions, right? So make sure that you read first, okay? So if we do F4-13, we actually have an image in the book. I'm going to try to, I cannot project when I am recording. Or can I? No, I can't. I tried it last time. Do you have your book with you? All right, then you're going to have to see me draw this figure if you don't have your book with you. Essentially, it's a three-dimensional figure in X, Y, Z space. I'm going to draw my x-axis, my y-axis, my z-axis. I have a pipe, right, that moves or that is 0.3 meters long through the x-axis, along the x-axis. And then it flips around, it turns 90 degrees, and moves 0.4 meters along the y-axis. And then it points directly downward along the z-axis and moves 0.2 meters. So it's a three-dimensional pipe. Don't get confused. This is x-axis. Then it turns 90 degrees and moves along the y-axis. Then it turns another 90 degrees and moves along the z-axis. So this is my pipe.
Could you repeat which problem number is it?
4-13. I'm going to call my origin O. I'm going to call this point A. I'm going to call this point B. Now, this is a rigid pipe. Remember we said in the first week that statics will focus on rigid bodies, bodies whose shape do not change. If I were to apply a force at the bottom of the pipe, just a force F, I'm going to see if I can figure out the moment from that force. So let's suppose that my force F, my force vector, is equal to 300I minus 200J plus 150K. And this will be in newtons. So I have my force and I have this pipe. Now there's different things I can ask you, but let's go with the problem statement first. 413 says determine the magnitude of the moment that this force causes about the x-axis. So let's think for a second. We want the magnitude of the moment about the x-axis. I think it was this problem as a test last semester, or at least this figure. And I asked for students to give me the magnitude of the moment of the force about the x-axis, just like the book. And I would say about 25% of students calculated the moment of this force, basically drawing a straight line from O to B. So that didn't really tell me anything, because I wanted the moment of the force about the x-axis. So how do we solve this problem? What do you think? I mean, we can still write down the equations that we know and maybe figure out how we can get what we need from those equations. So what do you think? Any ideas?
My mind goes to using the cross product.
Okay, so your mind goes to using the cross product.
But
Okay.
I also see that since it's only about the x-axis,
Okay.
that a lot of values would just cancel out.
Okay, I like the way you think, right? You want to use the cross product, but it's only about the x-axis, so you know that some values are just going to cancel out immediately. So let's look at that, okay? So Noah is saying, I want to do the cross product, but I feel that some values are going to cancel out. We have 8 minutes left. Let's figure out which values cancel out. We have time, okay? So if we're doing the cross product, we have our force vector, so that's good. What would the position vector be for our cross product? Remember, the moment about the x-axis. So what's the position vector, or what position vector can I use for the x-axis?
Just the position vector of whatever that distance is on the x-axis.
Okay, so here's where we need to perhaps try to visualize this in terms of moments. So because we want the rotation about this axis, right? We can't assume that by using a position vector, setting a position vector along the axis, that it will suddenly intersect with the force. There are some ways that we can do that. However, remember that when we express our moment as a vector, what we have is an x component, a y component, and a z component. The x component of this vector, right, is r cross f. The x component of this vector tells me the rotation about the x-axis. The y component tells me the rotation about the y-axis. The z component tells me the rotation by the z-axis. So we are right in that we only need one component of this moment. But to calculate this moment, we still need the position vector that considers all of them. Okay? There are going to be easier ways, and we're going to learn them as the class progresses. But right now, I don't want you to get confused. I don't want you to think that because we only need the x-axis, our position vector somehow changes towards the x-axis. So the position vector is not what's going to change. What's going to change is the component of the moment that we select in the end. Okay? So let's look at our position vector. I'm going to restate the question. What is my position vector now? You know that the position vector, I can't just say it's the x-axis.
Right.
What's the position vector?
0.3 I hat.
Okay.
0.4 y hat, and negative 0.2 k hat. Excuse me, j hat. Then k hat.
Okay. Good. I'm not saying that you're all wrong, because you're not. But I want you to be very careful with this, okay? We only want the x component. That doesn't mean that our position vector needs to forget about everything else. It's at the end that we forget about everything else, okay? So we have R cross F. We can do the determinant, right? And I'm just going to do a quick review. What do I write in my second row? Not you, Tom, behind you.
Right, the first one, so it would be 0.3
There we go.
to 0.4 to 0.2.
That's correct. Thank you. Tuong, now you. What do we write in the second row, or in the last row? Sorry.
So the forces of 300, negative 200, and 100.
Good. We already know that cross product is I times this cross minus j times this cross plus k times this cross. So we can get a whole moment for everything, but we only care about the x component, right? And what is the x component of this moment? So if I were to ask you, you can solve it yourselves here, but kind of want to also finish on time. So if I were to ask you, what's the x component of this moment? Looking at this determinant, looking at this matrix, what's my x component? You don't have to give me the final number. Just tell me what I need to write down so I can calculate it.
0.4 times 1.5 minus negative 0.2 times negative 200.
Good.
I.
Good. So we don't have to calculate the y component and the z component because we'll only ask for the rotation about the x-axis. However, for the position vector, we cannot ignore, right, the location where the force acts on. Okay? So plug those numbers in, and please tell me what is the moment about the x-axis. We have 0.4 times 150. Is that 60?
Yes.
Okay. And then we have minus 2 negatives form positive, so minus 0.2 times 200. Is that 40?
Yes.
Okay, so what's 60 minus 40?
20.
20 what?
Newton times meters.
Okay, newtons times meters, and that's my component in the x direction. I want to note a little mistake here. I wrote I here, but remember that the component is only the magnitude. There's no need to write I, okay? I mean, we know that it's I, but there's no need to write it down, okay? Just wanted to note that little error here. So 60 minus 40, we get a rotation of 20. Is this positive 20? So that means that the rotation will be, okay? You may be a little bit, confused because if you look at this, it kind of seems like this force is coming underneath it, but focus on the components, right? If you look at these components, then you see that the force actually passes a little bit above the x-axis, okay? So try to look at things in terms of vectors, not so much graphically. When you look at the graph, it can be tricky, right? So try to look at your vectors, your components, in order to understand your signs and your orientations. Any questions before we wrap up? What's your name?
My name's Ryan.
Are you good? You understand everything? If I give you a test next week, Monday, will you solve it?
Let's see.
Okay, we'll see. That's a good answer. All right. So if there are no more questions, I will see you next Monday.